Hello, this video hopefully is going to make it a little bit easier to make measurements using the Multisim software, especially using the Tektronix oscilloscope. So I'm starting off here with the scope set up to measure a 10 kilohertz signal. Okay, and for a 10 kilohertz signal, you want to set the time base probably to around 50 microseconds per division. You want to see somewhere in between, say, 3 to 5, 3 to 10 cycles on the screen of the oscilloscope. Too few and you won't be able to read it properly, and same thing with too many. So let's say 3 to 10 would be okay. I prefer to have 3 to 5, but 3 to 10 will work as well. So on this scope, the way you change the time base is with this dial here, and you can see it as I move to the right and to the left. If I move it counterclockwise, it's giving me less time per division, and if I move it clockwise, it's giving me more time per division. You'll notice that you get a bunch of sine waves that are not in the across the screen. What you can do is click on single, and that will acquire another capture. So anytime that you get that, just click on single and that will fix that problem. So if I change the time base here, I'm at 50 microseconds per division. If I go down, see, that's not enough. Okay, and if you want to just fix that, click on single. The next thing that you will want to do is to change the volts per division, and that will be done with this dial right here. And the top channel, which is my input, is channel 1, and it's the yellow trace. Channel 2 is the blue trace. And so right now tells you right here that channel 1 is set to 200 millivolts per division. So that's telling me that from the center of the sine wave up to the top would be 200 millivolts. So it's 200 millivolts peak, or 400 millivolts peak to peak, and 200 millivolts times 0.707 is what's giving me the 141 millivolts RMS. Now, let's say that your input changes and the signal is like this, way too high. Well, you can adjust the volts per centimeter so that you get an appropriate amount of divisions on the screen, and anywhere from 2 to 3 to 4 would be okay. So what I'm seeing here is not bad. This would be maybe too small, or sorry, that one's too large, and that might be a bit too small. So kind of adjust it so you get, 2 to 3 would be appropriate. Now, I prefer to see the two channels not overlapping each other like you might see. Let's see if you can move this manually. Nope. But one of the things you might want to do is move the position of the trace, and that's what this position dial is for in the vertical. And you can see as I rotate it, it comes on top of the other one. Now, it's not terrible to see them overlapping, but I generally would not want to see them overlapping, so bring it down. And for this lab, what's more important is that we're trying to measure the RMS value of the input on channel 1 and compare it with the output on channel 2. You'll notice as you move this dial, either clockwise or counterclockwise, moving it counterclockwise is moving it down, and it actually tells you how many divisions and how many millivolts it's down. And it's best to put it on a line so it's not halfway. So I'm going to move this so it's more appropriate. I'm going to move it down. I think it kind of locks in there. We're not there yet. And sometimes the mouse goes away from the dial. So that's good because we're at 2 divisions down, or since we're at 200 millivolts per division, we're 400 millivolts down. So that would be a good setting for the vertical. Now let's look at how we set up the measurements, which is over here. And as I said, what I want you to measure are the channel 1 frequency, channel 1 RMS value, and channel 2 RMS value. So that way we can calculate the dB difference, compare the input versus the output. Now let me show you how to do that. So I start off by clicking up here on the measurement, and maybe let's start off with just a new screen. So here I don't have any measurements right now, so let's see how we add them and actually make the measurements. So the first thing to do is click on Measure, and then click on the top channel 1. So it says channel 1 none right now. So I click on this button. And the source cycles through here. So this scope has 4 channels. We want channel 1. And we want to measure the frequency on channel 1. So I just click on frequency and it's telling me that it's 10 kilohertz. So that's one measurement. The next thing you do is go back up to measure, select the next button, and this time we do want channel 1, and we want to keep going through this sequence till we get cycle RMS. So that's channel 1 RMS, which is my input in this case. Click on measure again and go to here. If you have to change the channel, this is where you'll do it. So in this case, we want channel 2, and we want to measure the RMS value of channel 2. So I just keep cycling here until I get that, and it's 110 volts RMS. And then when you're done everything, you just click on measure again, and you see all the measurements. And this is what is going to be most critical when you verify the operation of the filter. So for example, with this particular filter, I think the critical frequency is about 11.5 kilohertz. Now let's look at that, because the input is, you can see it here, is 200 millivolts peak to peak. And maybe I can add that here. Let's add the peak to peak value of channel 1, or at least the peak. So click on channel 1, measure, and let's see if there's just peak. Maybe not. Okay, we'll just do that. So it's showing as 398 millivolts peak to peak, and that makes sense because our generator is set to 200 millivolts. So this is at 400 millivolts. So I'll stick with that, go back to measure, and now it's got each one of these. So to figure out the RMS value, at least to calculate it, what you would do is multiply the peak value, which is 200, by 0.707. Okay, and that'll give you the RMS value. So now that we've done that, let's go back up here, and I think we've done everything that I want to do here. The only thing I'm going to change is the frequency. So I'm going to stop the simulation. And I almost always stop the simulation between making a change, but that's okay. You don't have to do that. And I'm going to choose 11.4 kilohertz. I'm going to run the simulation again. And notice that my channel 2 RMS value is about 100 millivolts, or very close to it. And if you multiply 141 millivolts times 0.707, and that's actually 1 over the square root of 2, that's going to give me my minus 3 dB point, okay, in voltage. So 141 times 0.707 gives me about 99. Okay, so that tells me I'm at the critical frequency, and that's something that I'll want you to set up as well. And it's based on the maximum output. And let me show you the maximum output. Since this is a low-pass filter, we're going to put in a low frequency. So I'm going to set this to 1 kilohertz. I'm going to stop and rerun this again. Now, notice what happened is the frequency changed to 1 kilohertz. So the time base here is not set up correctly for a 1 kilohertz signal. We should be closer to 500 microseconds. So I'm going to set it for 500, maybe even 200. And as I said, when this doesn't refresh properly, just go back up here and select, where am I? Single, I think it's single trigger. And maybe that's not enough, so we'll just go back here. Sorry, the other way. Single again. And now that makes a little bit more sense. Now notice compare the input versus the output. Well, they're exactly the same. They're 141 millivolts. And this makes sense because this is a low-pass filter. Low-pass filter that's passing the low frequencies and attenuating the higher frequencies. And I can show you that with the higher frequencies. Let's go up to 100 kilohertz. Okay, stop and run that again just to refresh. And you'll notice what happened here is that since we're at 100 kilohertz, we probably want to be at 10 microseconds per division. So I've got to go backwards on this dial. And that's 200, That's reasonable. I can do a refresh of that. Now notice what happened to the output here. Went way down because now we're filtering those high frequencies. They're cut off. They're attenuated. Okay, and dramatically in this case, we're down to 2 millivolts. All right, I hope all of this helps when you're doing lab number 2. Thank you.